This will be a short video on something that you really already know about, homomorphisms, group homomorphisms. A mapping phi from G to G prime is called a group homomorphism if it simply preserves the group operation. So you've seen this before. We know that isomorphisms do this. But isomorphisms have to be one-to-one and onto. So this is exactly the same thing as you've learned before, one of the properties of isomorphisms. But this phi is not necessarily one-to-one or onto. So we need two new definitions. Since G is not onto, we're going to define a set, a subset of G prime, called the image of G in G prime. And let's see, I'll draw a circle in here to represent phi of the set G. So you know, if there's a set in the parentheses there, it doesn't mean that phi is mapping an element G. It is the image of the entire group G. So let's see, I could draw our map phi like this maybe. So you see that phi maps G onto phi of G. Now the other definition that we need, because phi is not one-to-one, is that there may be, we know that E prime is in here, because phi of E will be E prime, just as it was in the isomorphism. But not only E will map to E prime, maybe, but maybe not. So we're going to consider the subset called the kernel of phi, K-E-R, phi. The kernel is a subset of G, and the kernel consists of the elements of G that map to the identity of G prime. So look very carefully at these definitions. Phi of G, the image of G, is the set of all phi of G for G in G. That's the red circle. The kernel of phi is the set of all G in G that get mapped by phi to the identity. So those are two new sets that will be very important in our discussion of homomorphisms. So let's look at an example. Here, phi is a mapping from the general linear group to the non-zero real numbers. And it is taking a matrix and mapping it to its determinant. We know that all the matrices in GL2R have non-zero determinant. So the mapping makes sense to go from the general linear group to R star, the non-zero real numbers. Well, the first thing we should do is prove that it is a group homomorphism. So we'll take two matrices A and B in the general linear group. So let's say phi of AB. We know that the operation in the general linear group is matrix multiplication, and that will be, by our definition, the determinant of the matrix AB. From your linear algebra, you know that the determinant of the product is the product of the determinants. So that is the product of two non-zero real numbers. It's a non-zero real number, and in fact it is equal to phi of A times phi of B, multiplication in R star. So we see that phi does preserve the operation. Now let's see if we can determine those two sets. The subset of the general linear group that maps to the identity 1. Well, we know that phi of phi of A will map to 1 if the determinant of A is equal to 1. In other words, if A lives in the special linear group of 2 by 2 matrices, entries from R. So the kernel of phi, ker phi, the subset of the general linear group that gets mapped to the identity of R star, is the special linear group of 2 by 2 matrices. That's the kernel. Now, what about the image of the general linear group? Well, in this case, you know that you can take any non-zero real number and easily find many matrices that have that number as their determinant. So in this case, phi is onto. And we can say if phi is onto, another way of saying that is that the image of the group GL2R is R star. The next example is a group that we haven't talked about before. It is the group of all polynomial functions with real coefficients under the operation of addition. So you should be able to verify that this is a group. We won't bother to prove it, but let's take a moment to remember what is a polynomial and what would be the identity and inverses in this group. A polynomial is like I have written here in blue. The a sub i's are the coefficients. So the a sub i's come from R. They're just real numbers. And it is of the form a0 plus a1x plus a sub 2x squared plus dot 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 plus a sub n x to the n. So n is called the degree of the polynomial, and it is greater than or equal to, well, not 1, 0. If we have a 0 degree polynomial, then we just have a constant function, horizontal line. If we have a linear, then it is of the form a0 plus a1x, degree 1, or a quadratic, degree 2, etc. So you've been familiar with these for a long time, but now think of all of them and with the operation of addition. So what would the additive inverse of p of x be? Well, it would be minus p of x, which would just be minus a naught plus, minus a1x minus dot 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 minus a sub n x to the n. So it's just multiplying p of x times minus 1. That gives you the additive inverse. And the identity now, it's not I of x equals x. That's when multiplication, or function composition, is the operation. This is just simple addition. So the identity, I'll call it I of x, but it's simply the constant polynomial whose graph is the x-axis. So Rx is a group. And once you understand what the group is, then let's look at this mapping, phi. Phi maps the group to itself by phi of f, some polynomial, is equal to the derivative of that polynomial. Well, you know that polynomials, derivatives are also polynomials, so this does make sense. Just look at a quick example. Like if we have phi of 3x cubed minus 9x plus 1. Well, that's just going to map to its derivative, 9x squared minus 9. So it just simply maps a polynomial to its derivative. This is quickly seen as a homomorphism because you know that phi of f plus g, two polynomials added together, is f plus g prime, which is the sum of the derivatives, which is phi of f plus phi of g. So therefore, phi is a group homomorphism. Now let's find its kernel, and let's find the image of phi. Well, phi of Rx. What is the image of the entire group? Well, is it onto? If we pick a polynomial, any polynomial, it has an antiderivative. It has infinitely many of them. So this is definitely onto. Phi of Rx is equal to Rx. And if you wanted to prove that, you could say, let f be in Rx. Now I could write out f as a0 plus a1x plus ... But I don't need to, because you remember the fundamental theorem of calculus tells you that if you take f and you integrate from a to x, little f of t dt, that this gives you a whole family of functions, in fact, that map to, that have f of x as their derivative. So we have a whole family of functions that map to f of x, and certainly phi is onto. Now, what about the kernel of phi? The kernel of phi will be equal to the set of all f in Rx, such that phi of f is the identity, the zero polynomial. Well, in other words, f prime is equal to 0. That's the kernel. And this will be all constant polynomials, all polys of degree 0. In other words, all constant functions. Like if f of x is equal to 6, f prime of x is equal to 0. So that is the kernel, and we found that it is onto. The next example asks us to explain why, if phi maps r star to r star, operation multiplication, non-zero reals, by phi of x equals x squared, it is a homomorphism. Well, let's look at that one. So let's say phi of xy, where x and y are two non-zero real numbers, is equal to xy squared. But we know it's an abelian group. It's x squared y squared, and that is phi of x, phi of y. So this is a homomorphism. The kernel of phi is equal to the set of all numbers whose square is 1. So the kernel of phi in this case is just the number contains 1 and minus 1. And in this case, phi of r star, the image of r star under phi is equal to plus, that would be it, all the positive real numbers. Every positive real number has a square root. Now the other example of phi, do that over here, where if phi is mapping, I should have called it something else, if phi is mapping r to r, and now you know that the operation is addition in just the real numbers, it is not a homomorphism. Well, it's easy to see why not. Phi of x plus y, which is equal to x plus y squared, which is equal to x squared plus 2xy plus y squared, is not equal to x squared plus y squared. So phi of x plus y is not equal to phi of x plus phi of y. We have 6 properties of homomorphisms, and they are very similar to the 6 properties we had of isomorphisms. In fact, the proof of these first 2 properties, those are exactly the same as the first 2 properties of isomorphisms. Number 3, if the order of G is finite, then the order of phi of any one of its elements, phi of G, divides the order of G. Okay, well, let's prove that. If G is finite, we can say let the order of G be n. Certainly all of its elements have finite order. Then, since we have property 2, since phi of G to the n is equal to phi of G to the n, and we know that phi of G to the n is equal to phi of E, this implies phi of E is equal to phi of G to the n, and phi of E is E prime. So phi of G to the n is equal to E prime. And that means that the order of phi of G divides n, the order of G. Remember when we talked about isomorphisms, the order of phi of G is exactly the same as the order of G. But with homomorphisms, where they are not one-to-one, necessarily one-to-one, the order of phi of G might be a divisor of the order of G. Now we're going to show that the kernel of phi is a subgroup of G. And so let's recall what it is. It is the elements in G that map to the identity. It might be just E, but that's certainly a subgroup, the set containing E. So let's prove in general that the kernel of phi is a subgroup of G. So we'll start like we always do. Let x and y be in the kernel of phi. And we want to show, let's put a little thinking bubble down here. We want to show that x, y inverse is in the kernel of phi. So in other words, we want to show that phi maps x, y inverse to E prime. So that's what we hope to end up with. But let's just go back up here and start writing things that we know. If x and y are in the kernel of phi, well, let's look at phi. Let's just start. Look at x, phi of x, y inverse. Phi is a homomorphism, so that is phi of x, phi of y inverse. Property 2 tells us that this is phi of x, phi of y inverse. Property number 5 tells us that if phi of A is equal to phi of B, if and only if A and B are in the same coset of the kernel. So let's prove this. This is an if and only if statement. So let's start with phi of A equals phi of B. I'm just going to do this all as if and only if, because the proof just works backwards exactly the same way. So phi of A equals phi of B means that phi of B inverse phi of A is equal to E prime. Well, it's a homomorphism, so this is true if and only if phi of B inverse A is equal to E prime, which is true if and only if B inverse A is in the kernel of phi. But the kernel of phi is, of course, if you look at a factor group, this is a coset, and this is true if and only if, from our properties of cosets, that A, the kernel of A times A kernel phi is equal to B, is equal to this coset. They are the same. So listen to the words again. A homomorphism maps two elements to the same image if and only if those two elements of G are in the same coset of the kernel. number 6 is a little bit confusing in the notation. We know that phi is a homomorphism from capital G to capital G prime. So it's not necessarily one-to-one. And it doesn't make sense to assume that it has an inverse function. And indeed, this phi inverse that you see here, this is not talking about phi inverse of an element G prime. We have no idea if there is a phi inverse. What this is, and let me write it out in words, this is the inverse image of G prime. In other words, it is the set of all elements in capital G that map to G prime. Maybe an example. How about phi inverse of E prime? What is that? Well, that's the kernel of phi. It's the set of elements that map to E prime. So property 6 tells us that if we know phi of G is G prime, then the inverse image of G prime, the other elements that map to G prime, are G, the elements in that coset, G kernel phi. If phi of G is G prime, then everything in G kernel phi maps to G prime. That's what we want to prove. Well, I circled the two sets. We're assuming that phi of G is G prime. And I want to show that these two sets are equal. So if I was going to be super careful, I would show inclusion going both ways. But this also could just be proved with a straight if and only if proof, because each step is just in reverse when you go the other way. So we know this. We know phi of G is G prime. And now let's well, I won't say let. I'm going to say X is in the inverse image of the element G prime if and only if phi of X is equal to, well, phi of G is equal to G prime. We were given that phi of G is G prime. X in the inverse image of G prime means phi of X is G prime. Well, this is a homomorphism, so phi of G inverse phi of X is equal to E prime, because phi of X equals phi of G. So multiplying on the left by phi of G inverse, we get this. And this is an if and only if statement. But it's a homomorphism, so that means this is true if and only if phi of G inverse X is equal to E prime. And that's true if and only if G inverse X is an element of the kernel of phi. It's mapped to E prime, so it lives in the kernel. And what we learned about cosets, this is true if and only if X lives in this coset, G kernel phi. Now, since all of these were if and only if statements, it's just different ways of saying the same thing. We didn't apply any theorems or anything. We're just using the definition of these different sets. Since these are a series of if and only if statements, we can say then X lives in the inverse image of G prime if and only if it lives in G kernel phi, so we can conclude then that the inverse image of G prime is equal to G kernel phi.